Welcome to Adventures in Math. In today's adventure, we explore different kinds of infinities and numbers. We'll see a naturally emergent hierarchy and how it connects to the concept of counting and infinity. First, let's look at the numbers most familiar to us, the counting numbers, or natural numbers. When counting, we start at 1, and then add 1 to get the next number. For example, 1 plus 1 is 2, and then 2 plus 1 is 3, and so on. We'll refer to the symbol script n as the set of natural numbers, using braces containing the sequence 1, 2, 3, 4, 5, and so on to show what is contained within the set. Since we can always add 1 to a natural number to get the next largest natural number, there is no upper bound on how many natural numbers there are. We often refer to this concept as infinite. However, as we will see, there are multiple magnitudes of infinity, where some infinities are conceptually smaller than others. Let's explore this concept further with an example. Now that we've hinted at there being bigger and smaller infinities, let's look at the set of natural numbers again. What might be a bigger infinity than the number of natural numbers? The integers seem like a possible candidate, since they include what appears to be more numbers than the naturals, since we have negative values and 0 included as well. Now we have a hypothesis that the set of natural numbers has less elements than the set of integers. To determine if the two sets are of equal size or not, we need to show whether or not there is a one-to-one correspondence between them. If we can match up or map each element of one set to unique elements in a second set, and no elements are left out of the matching, we have a one-to-one correspondence, or a bijection. In this example, we have two sets, x and y, consisting of 1, 2, 3, 4, and A, B, C, D, respectively. We illustrate one possible one-to-one correspondence with arrows from elements of the set x to the set y. If we can assign a unique natural number to each integer, or more simply count them, then we can show that a one-to-one correspondence exists between the integers and natural numbers. In this illustration, we start at 0 and label it with the natural number 1. Then we proceed to move to -1 and label it with 2, and then on to 1, labeling it with 3, and so on. We can bounce back and forth through the integers to assign a natural number to each, and therefore we have a one-to-one correspondence. This means that there are just as many natural numbers as integers. These two infinities are the same size, or cardinality. Let's try something else. Positive fractions or rational numbers use two natural numbers in their definitions. Maybe there are more of them, a bigger infinity. We'll call the set of positive rational numbers script q plus, using what is commonly called set builder notation, since writing out every positive fraction in a sequence would be cumbersome. We can read this notation in English as the set of positive rational numbers contains every fraction a over b, where a and b each come from the set of natural numbers. From this definition, it may seem like there could be more rational numbers than natural numbers, since it takes two natural numbers to describe one rational number. However, this is not the case, and in fact, the two sets are equal in size. We'll proceed to define a one-to-one correspondence between the two sets, or simply show that we can count the positive rationals. To see this clearly, let's define a mapping from rational numbers to the familiar xy coordinates, where the coordinates will stand in for the numerator and denominator of the fractions. First, we draw axes for a and b. Next, let's look at a few concrete examples. The coordinates 1, 1 correspond to 1 over 1. Similarly, the coordinates 1, 2 correspond to 1 over 2, and 2, 1 corresponds to 2 over 1. Now let's choose 7/3. Notice that it corresponds to the coordinates 7, 3. Now that we've established the idea of mapping fractions onto coordinates, let's see how we can count them. We start at 1, 1, labeling it with the natural number 1. Next, we move on to 2 over 1 and label it with the natural number 2. Now we'll continue to zigzag in this fashion through the grid of coordinates. In this illustration, the grid is only 9 by 9, but we can extend this strategy conceptually to count all of the positive rationals. So far, we've seen the natural numbers, the integers, and the rationals all share the same size or cardinality. This is somewhat counterintuitive, since the naturals are a subset of the integers, and the integers are a subset of the rationals. The subsets are the same size as their containing sets. The next logical step in this hierarchy of numbers is what are called the algebraic, or specifically the real algebraic numbers, which are real valued roots of rational polynomials, like the golden ratio phi, which we encountered in our last adventure. The set of algebraic numbers also has the same cardinality as the naturals. Now we will encounter a bigger infinity. The real numbers includes everything we've seen so far, with some numbers even transcending finite algebraic descriptions, like pi or e. So far, we've been finding one-to-one correspondences to show equal cardinality. We need to change our perspective a little now so that we can instead show that no such correspondence exists between the natural numbers and the reals. First, let's select a subset of the reals, the interval 0 to 1. Imagine listing out every number between 0 and 1 in an infinite table. The order that we list them in is not important. For numbers with decimal expansions that terminate, like 0.42, we will fill in the rest of the row with zeros. If there is a one-to-one correspondence between the reals and the naturals, we should be able to count the number of rows in this table. Now we will show that we cannot possibly have all of the reals in the table. Let's add a new row to the top of the table. We will construct a new number that is different from every other number in the table by moving diagonally through it. First, we see 4. Let's pick a digit for our new number that is different from 4. Let's arbitrarily choose 5 because it is not equal to 4. Now we differ from the first row of the table by at least one digit. Moving to the next row and down the diagonal, we see the digit 1. Let's keep things simple and choose 2 for the number we are constructing. Now our new number differs from the first 2 rows of the table. Let's continue this process, moving to the next row and down the diagonal, always choosing a digit for our new number that is different from the current digit. If we play this process out, we will construct a real number that was never in the table. Therefore, we have reached a contradiction and can conclude that it is not possible to count the real numbers with the naturals. There are more real numbers than naturals. We have encountered a bigger infinity. We call the size or cardinality of the set of natural numbers a countable infinity, and give it a name, aleph naught or aleph 0. The real numbers can be shown to have a cardinality of 2 raised to the aleph naught. There are infinitely many more infinite cardinalities, aleph 1, aleph 2, and so on, but without making some special assumptions, we cannot determine where the real numbers fit into this order. Since we cannot prove that there are no sizes of infinity in between the naturals and reals. We can say these are uncountable infinities, though. In today's adventure, we encounter different sets of numbers and how their sizes or cardinalities relate to different kinds of infinities. In case you were wondering about complex numbers or other types of numbers like quaternions, don't worry, we're sure to encounter them along our adventures as well. If you enjoyed the video, don't forget to like and subscribe.